This is going to be a review of trigonometry and angled velocities practice. So we are going to go through some crucial trig skills to understand how to do angled velocities. So looking at this here, the first thing we have to understand are our trig equations. Sometimes you might have heard these called SOHCAHTOA. That's just a way to remember them, okay? But what they are is the sine theta is equal to the opposite over the hypotenuse. The cosine theta is equal to the adjacent over the hypotenuse. And the tangent is equal to the opposite over the adjacent. Okay? Knowing these equations are crucial in understanding how to solve these problems. So when we refer to opposite, adjacent, hypotenuse, those sorts of things, it's important to understand what side of the triangle we are talking about. So that all comes down to what angle you have and where your 90-degree angle is. Your 90-degree angle is the biggest angle, okay? Your hypotenuse is always across from your 90-degree angle, okay? Across from your 90-degree angle. So that is our hypotenuse. The opposite side and the adjacent side depend on what angle you are given. So it says to draw and label where the opposite and adjacent side are with the given angle. Our angle is here. Adjacent means next to. So this is our adjacent angle. Our adjacent side. It's adjacent to our angle. And then this is our opposite side because it is opposite from our angle. Okay? These two things, understanding the equations and understanding how a triangle is set up to use those equations is really crucial in understanding how to do or figure out these trigonometry sort of problems. So looking down, it says solve for the following given the triangle information below. Okay, so let's draw a picture of what our triangle is. We have a triangle here. We know our angle is 25 degrees and our hypotenuse is 13. So our hypotenuse is across from our angle or our 90-degree angle. Okay, so that's our hypotenuse. Our opposite side is opposite of our given angle. So 25 is our given angle. This is our opposite side. Our adjacent side is right next to it. So how do we use these trig equations to help us solve these? We have to think about what we're given. Here we know our angle and our hypotenuse. If we're looking for our opposite side, we need to use sine because sine uses opposite and hypotenuse. So sine of our angle, 25, is equal to opposite divided by hypotenuse, which is 13. Multiply 13 on both sides and you get opposite equals 13 times the sine of 25. You're just multiplying 13 on both sides there. And then you get your opposite side is equal to 13 times the sine of 25. And you get 5.5 basically. Your adjacent side is, we're going to use our cosine equation because cosine of our angle is equal to adjacent divided by hypotenuse. Our hypotenuse is 13. Okay, adjacent divided by hypotenuse. So again, I'm going to multiply 13 on both sides. And you get adjacent is equal to the cosine of 25 times 13. You can type that into a calculator. Cosine of 25, and you get that is equal to 11.78. Okay, let's look at one more example where you're solving for the angle, and then you'll have a chance to practice some on your own. So if we come here, we have a few different problems where it just gives you the triangle. You're getting practice using sine, cosine, and tangent. So here, we have to be able to identify each of our sides again. So our angle here, this symbol is just a theta symbol. Okay? Theta is a common variable that we use to indicate that it is an angle. Okay, an angle. Okay, so theta is a common symbol that we use for an angle. So right now we are trying to solve for theta. Let's think about what sides we have in relation to where the angle is and where our 90 degree is. So across from our 90 degree is our hypotenuse. So this is our hypotenuse, and then this is our opposite side. This is our adjacent side. So we're looking for theta. I have my opposite and hypotenuse, so I'm going to use the sine of theta equals opposite over hypotenuse. Opposite is 6 over hypotenuse, which is 11. If theta is trapped inside of here, we have to do the opposite of sine, okay? The opposite of sine is called inverse sine. So if you take the inverse sine of both sides, you get theta equals the inverse sine of 6 divided by 11. You can do this on your calculator if you use the second button, then hit your sine button. You're going to see it puts an inverse sine, and then type in whatever you need to. In our case, 6 divided by 11. And you're going to get an angle equal to 33.06 degrees, okay? So about 33 degrees is what our angle is for this triangle. Okay? So I want you to go through, practice those other ones, get used to using sine, cosine, and tangent, and you need to first identify what all is given to you. So I'll do that on the next problem for you, and you can finish it. Across from our 90 degree is our hypotenuse, and then we know this is our angle, so this is our adjacent side, which is what we're looking for, and this is our opposite side, which we don't need to worry about for this problem. Okay, same here. This is our hypotenuse. This is our angle. So this is opposite and this is adjacent. Okay, so you're using tangent here because you're given opposite and you're trying to find adjacent. So go through and see if you can identify what each of your sides are and then solve for whatever your unknown is. This does apply to what we've been doing because we've been looking at angled speeds. So in this problem, we have some angled speeds, or we have an angled speed of a high jumper or a long jumper, and we need to use that to help us move forward. So part one of this problem says you want to solve for the horizontal and vertical components of the speed. Says Sam is a long jumper and jumps an initial velocity of 2.8 meters per second and at an angle of 20 degrees to the horizontal. So what this looks like is our hypotenuse, which is our angled speed. V equals, this is our initial speed, 2.8 meters per second. This angled speed would not happen unless we had part of it in the x direction, so this is Vx, and part of it in the y direction, this is Vy. Okay, so part of our speed is made up in the x direction, the other part is made up of the y direction. Whatever you have on your hypotenuse, this is an angled speed, is the same units, is the same variable you use for your x and y. So since this is a speed, this is our x speed and our y speed for this vector, okay, for this angled vector. So to solve for x and y, we need to use our trigonometry equations. And this is 20 degrees here. So Vx is what we're going to solve for first. Vx is adjacent to. So we're going to use the cosine of 20 equals adjacent Vx divided by hypotenuse 2.8. Multiply both sides by 2.8. And I get Vx equals 2.8 times the cosine of 20. And I should get Vx is 2.63 meters per second. Okay. Vy, we're going to be doing the same thing, except for Vy is opposite. So now we're going to use sine of 20 equals Vy divided by our hypotenuse, 2.8. So Vy equals 2.8 times the sine of 20. And you get Vy equals, not 9, it is 0.957 meters per second. Okay, so that's solving for the angled velocities. Very similar to what you were just practicing up above. Okay, but understanding that if we have a velocity on our hypotenuse, that angled velocity is made up of a velocity in the x direction and a velocity in the y direction. Okay, I have to have some sort of speed in the x and y to get to that angled speed. Okay, awesome. So now we are going to look at, we need to draw a picture of what is happening in this problem for part 2. So when we go down here, we're going to draw a picture. We have Sam, and she's jumping at an angle here. And she is jumping at this angle and landing some distance away here. This is going to be our delta x distance. This is the goal in long jump. You're trying to get the farthest delta x. So just an idea of what's happening here with this angled speed traveling this delta x. We can see that this is just kind of emphasizing this is projectile motion. Okay, this is projectile motion. Okay, so let's go up to part 3 here. And now we're actually solving for how far horizontally she traveled if it took them 1.2 seconds to land their jump. Okay, so x versus y. Well, we know the time t is 1.2 seconds. That could go on both of them. T equals 1.2 seconds. That's our total time. We know that our Vx is equal to 2.63 meters per second, and our Vy initial is equal to 0.957 meters per second. And then we are looking for delta x, okay? So we don't really need to worry about our y components because we are looking for delta x, and we have everything we need to solve for delta x. The equation we're going to use is Vx equals delta x divided by delta t. So plugging that in the wrong area. Let me erase that. 2.63 equals delta x divided by 1.2 seconds. I'm going to multiply 1.2 seconds over, so I get delta x equals 1.2 times 2.63. 2.63. So you get a delta x equal to 3.157 meters. 3.157 meters. Okay. So that is our delta x. Okay, that is our delta x. The last question it is asking you about how could Sam improve their long jump. Okay, so improving their long jump means we want to get a greater delta x. Okay, what we would need to do to improve our long jump is we would need to jump at the same angle with a greater velocity. That would improve our delta x. Or we could play around with the angle a little bit. But what we essentially need to do is we need Vx to increase in order to increase our delta x. So in some way, whether that's jumping at that 20-degree angle with a greater initial velocity, that's going to increase our Vx. Or if we are jumping at a different angle, we need to find an angle that would increase our Vx in order to increase our delta x. So how could Sam improve their long jump? They could jump a little bit faster or start with an initial speed a little bit quicker. That would improve their long jump.